Swayam Prabha. Digital India. Educated India.
Let's continue what we were discussing in the last class. We were looking at the forces that act on a vehicle as the vehicle goes over a ramp or a slope. One of the key things that we discussed in the last class was about the rolling resistance of the tire. There are a number of questions after the class. I would like to explain that again, so that you are clear about how we have converted the rolling resistance, the phenomena of rolling resistance, into a force. In fact, this was the key question that was asked after the class. Let me explain that again. We talked about equilibrium with the pressure, inflation pressure. We will come to that later. The only point which I wanted to make is that every part of the tire has to be under equilibrium with the load contact pressure that is acting as well as the inflation pressure. So, at the right at the center, when there is nothing else is happening, then the contact pressure should be equilibrated by the inflation pressure. We will talk about that when we come to the tire. I just wanted to make a passing comment. We will explain it later. Now, let us come back to this topic of rolling resistance. We said that the rolling resistance is due to viscoelasticity, right? And we said that that also results in an unsymmetric pressure distribution, right? We said that when the tire is stationary, standing, then it has to be a symmetric pressure distribution where a number of tread blocks are involved, and when it is rolling, when we follow a tread block, the pressure distribution due to a tread block will not be symmetric, because the loading and the unloading curves of a viscoelastic materials are different, and so it has to be unsymmetric. And we said loading curves being higher than the unloading curves, we said it has to be like this, and that this results in an unsymmetric force, the force which is the force that is exerted by the ground onto the wheel. That force is not going to be symmetric right at the center, but will be away from the center. We'll call this later, we'll call this, we'll give specific names to these things. We'll not do it right now, but let us understand first that there is a shift, there is a trail. Now, this force is the reality because of viscoelasticity. So, if I now want to shift the force to another place right at the center, I will have to do it with the force as well as a moment that is acting, right. So, if this is the direction of rotation and hence the driving torque's direction, then this force would give rise to a torque which opposes this driving torque, and so will be in that direction. It opposes the driving torque. The question that was asked is, how did I now replace this force by this force like this? And before that, how did I replace the driving torque force by a force like this, by a force at the ground? This was the question that is asked. Please, I want to take you back to the free body diagram. It's a very simple thing. So, we'll explain this with a very simple example, so that you understand small niceties of drawing a free body diagram. Suppose let's take that I have a tractor, okay, pulling a trailer, a horse drawing a cart, which is a very early example. Okay. Now, there is a link, okay, and now this tractor is pulling this trailer. Okay, which means that this tractor applies a force, okay, in this direction to the trailer. Now, if you want to draw the free body diagram of this tractor, what will you do? Apart from other forces, we will just neglect the other forces. If I have to draw a free body diagram, what will be the direction of the force? It will be in this direction. Okay? So, this will be the direction in which I will draw this free body diagram. So, in other words, I will look at the action of the trailer onto the tractor. Okay. So, what does the trailer do to the tractor is what I will look at and apply this. I will neither apply two forces in this direction, that means it cancels, that is ridiculous, okay, and I want to apply a force in this direction, then in that case it looks like trailer is pushing it, okay, there is no resistance. So, I will apply it obviously only in this direction. So, that is the reaction that you apply. In the same fashion, when the tire rolls, okay, it actually pushes the ground. You can imagine that it pushes the ground. You would have seen this when there is water or there is sand, it pushes the ground, okay, and so the force that it exerts on the ground will be in this direction, okay, like the force that is exerted here is in this direction. So, when I want to put the free body diagram now with the force that has to be acting on the tire, okay, which I want to represent now, or in other words the effect of road, like we have effect of trailer and tractor, okay, effect of road onto the vehicle, I have to put a force in the opposite direction. So, hence this force now becomes this. Clear? The force becomes like that. So, this is now the traction force, and that is due to the friction. Okay, we will see how friction holds this, right, that is the first one. Now, since the traction force is in this direction, I have substituted it with the force like this, okay, because of the effect of the ground onto the wheel, I have substituted it like that. I do the same thing for rolling resistance torque, which is produced by this force. Okay. So, when I shifted it here, I had a force in this direction and I also had that moment, and now that is very similar to the traction force. So, I replace it with another force that is acting like this. Okay. So, it is equivalent, same thing, same torque, which is that is the F rolling resistance, and that is the F traction. Clear? That is it. So, that is why we have two of them, okay, the front traction force and the rolling resistance force, which opposes the motion. Clear? Any questions?
What about the URW constant?
Yes. So, what is friction? What is friction coefficient? We will come to that in a minute. How does the friction act? We will come to that in a minute. Let us understand the forces that are acting. Okay. So, now that is the rolling resistance force. Right. Okay.
Why will there be a shift?
Yes, that is what we explained last class, that we will have a shift because of the viscoelastic effect, and that the loading, when tread block goes through loading and unloading, then the path followed are different. Okay, one is loading and another unloading. So, for the same displacements, okay, or the same strain, the forces that are given sigma are different, okay, and hence there can't be the same for the same, whether it is loading or unloading will decide whether the stresses are higher or lower, and because of which forces are higher or lower, and that is the reason why it can't be the same. So that's why there's a shift. Okay. Now, having come to this, we will go back to our equilibrium equations and write down the equilibrium equations for these things.
So, what decides the direction in which you draw that rolling resistance component?
Yes, yes. So, what decides what is this one? So, what is this force? What is the direction of this force? What is the direction of this force? Okay, that's the question. Obviously, when I am giving a driving torque, the force is in this direction. If I am giving a braking torque, okay, it will be in the opposite direction, right? Obviously, that's the thing. On the other hand, rolling resistance depends upon the direction of rolling. I am rolling it in, I'm rolling it like this. The rolling resistance doesn't care whether you are actually accelerating, decelerating, or doing neither of the two or either of the two and traveling at the same velocity. It doesn't matter to it. As long as there is compression and relaxation, okay, we are going into the viscoelastic effect, and that will give the rolling resistance, right? So, in either case, you will have that force here. So, interestingly, what really happens, which we pointed out in the last class, that the rolling resistance is something like braking, and so helps braking when the vehicle brakes, and it decelerates the accelerating vehicle, or in other words, it is, let's say, shall we say, a bad force that's acting. Either way, since it opposes the motion, okay, we are to compensate for this energy lost from the engine, and so it is a gas guzzler. It consumes energy, so it's a gas guzzler. So the best thing, it's a very, very important force now, especially if you look at passenger, whether it's a passenger car and commercial vehicles, especially in passenger car today, everyone wants very, very low rolling resistance. Okay, and when rolling resistance have to be low, you also get into one more problem. Because I said that it acts in the same direction of the braking force, so the braking force takes a beating, total force takes a beating. Okay? So, you have to be careful. In other words, we will see later that the tire itself, tire design itself is like a spider diagram. You can't improve everything. When we improve something, there has to be a sacrifice on something else, right? So, we will continue now. We will write down the equations here. Note that I'm up the hill, so I have W, this is W that's acting, and that is the theta s, which is the slope, okay. So, I resolve that. So, that becomes, this force become here, it becomes W cos theta s, and that becomes W sin theta s, and so on. One of the assumptions that we have made, obviously, is that cos theta is approximately equal to 1 in order to write this. Strictly speaking, okay, I have to now resolve it and put it, but I'm going to write that. In other words, I said that I will replace the rolling resistance force by means of a rolling coefficient, or rolling resistance coefficient, Fr into W. Actually, the W has to be in this direction, and so I have to actually resolve it and put it as W cos theta s, okay. But I'm assuming that cos theta is very small, theta is very small, so cos theta is equal to 1. So, I am just replacing this RRF as Fr into WF and so on, okay. Now, again, the rolling resistance coefficient, we are assuming that is the same in the front and the rear, okay. So, these are small assumptions. Now, we will write down the equilibrium equations.
Sir, earlier we said like rolling resistance is created due to normal force, but in the final free body diagram we are putting both normal force and
Yes, this is normal force, of course, exactly. So that's what I just pointed out, that we had a force which is away. When I want to now shift it to the center, then we will have a force, normal force will still be there, plus a moment, and the moment becomes the horizontal force, and the normal force is still there. So that's a reaction force, has to be there. Okay, that's the reaction force. Let's continue now. Let's write down two things we are going to do. One is, of course, the well known F is equal to ma. Okay, we'll write down F is equal to ma equation, and the other one which we are going to write down, that's the first set of equations. So let me write the other way. Ma is equal to the forces that are acting in the, I said that this would be the x direction, so we are writing this F is equal to ma, okay, in the x direction. So what are the forces that are acting? The two forces that are going to aid the vehicle to accelerate are the traction forces Ff and Fr. So these are the traction forces, and then the forces that are going to oppose the motion are the aerodynamic forces. Aerodynamic forces, as we are going to see now or later, is that it's proportional to v squared, velocity squared. So it's a very parabolic distribution. Okay, so at higher speeds they are going to be important. So there is a drag coefficient CD, and you're going to look at the projected area A, and you're going to look at v squared. Okay, so half rho A CD A v squared. We will see that a bit later. So we are now dumping everything as RA. Then I have the rolling resistance force, front and rear. I am combining them and writing them as the rolling resistance force. So what is the other force that's acting against it? It is W sin theta S, which we will call as the gravitational force, a resistance due to gravitational force. You can call that as Rg if you want. Right? And the other force which opposes is a drawbar pull. We will neglect that, we can add it if you want. Okay? Later we will neglect it. Okay? Drawbar pull is due to the force that's applied if you have a trailer attached to it, and so that's the drawbar pull. The next assumption which we are going to make is that h, which is the center of gravity height, is equal to HA is equal to HT. That's quite valid for a car, passenger car. So we're going to make an assumption like that. Right. Now my next job is to find out WF and WR. And WF and WR are determined by taking moments about that point A and this point B.
What is that RD?
That is a drawbar pull. In other words, if you have a trailer attached to it, okay, then that is the force. So I'm neglecting that. So how do we calculate WF and WR? Just take the moment about A. Okay, let's get that. I hope we don't miss out anything. So WF, let's look at this, WF into L, okay, the clockwise direction, okay, plus RA into H, Y plus, that's also in the clockwise direction. Look at the direction. If I make a mistake, it's up to you to point out. Okay, the onus is on you. Okay, so then what are the other forces? Rg, W sin theta, that's also in the clockwise direction, into H. Now I'm going to replace this Ma by means of, that is this force, by means of a D'Alembert's force, which is W by G into A, right. So when I replace that, then that's also in the clockwise direction. So G into A into H. I also have this force, which is W cos theta, okay, that force, and that force acts in the anti-clockwise direction. So I got to write that as, because it's in the anti-clockwise direction, write this as W cos theta S right into multiplied by L2 is equal to 0. Rearrange it, okay, but only a comment which I am going to make and which will be valid for the next class, this class and next class, is that you have to be careful with the sign here. It would vary whether you are going uphill or downhill, okay. So you have to be careful in that. So right now we are going uphill, okay, and so it has the same, so it opposes, so it's the same direction as that of RA, okay. If it's downhill, then the direction will be different, okay, will be opposite to RA. So good thing to do is to look at RA and where we stand, what's the direction, right. So write down, and other thing which we said is that we will make this to be equal to 1, sin theta will retain it, okay, so that we will get W 1 by L into WL2 minus the rest of the quantity. Why not you write that, okay, minus RA into H minus W sin theta into H minus W by G EA into H, okay. So I am just going to put minus or plus here to take into account whether it is going uphill or downhill, right. Write down for now WR, I will give a minute, write it down for WR, how will it be? Just take the moment about B now, okay, 1 by L we will have WL1 into cos theta, RA will become now plus RA into H. So all the directions will be different, plus minus W sin theta H plus W by G into A into H. Let me call this equation as 1, that equation is 2, equation 3. Simple equations, nothing, all of you can derive it very easily. Okay, let's rearrange this equation in a fashion that will be easier for us to interpret. Okay, so I'll write down that as WLF is equal to, I'll take the first term, okay, L2 by L, okay, the first term. So I'll put a minus sign there, minus H by L into, let me write down the rest of them, RA plus So how should it be? Just the same thing, but so that the sum has to be we will consistently use just plus or minus, okay, so that you will know when uphill, downhill, you will accordingly, you will do that, so that minus plus, plus minus, there will be a confusion. You can very easily find out which is plus, which is minus. So I'll consistently use plus minus. According to the situation, you will put plus and minus, okay, sin theta s plus w by g into a, right? Okay. Now let me call this as 4 and 5. I'll simplify the 4 and 5 equation by using equation 1, substitute that from the first equation, so that Wf is equal to L2 by L into W minus H by L. When I want to substitute that, so that I have F, okay, and when I substitute that, what would be that there? For RA, W, and RD, of course we have made it 0, and RG, so it will be, this will be F, so it will simply be, what will that be? When I substitute there in that expression, I'll have to bring all those rest of it to the third 3 terms to the right hand side, okay. So F minus RR, right, which I will replace by FR into W. Obviously WR will be L2 by L W plus H by L into F plus, F minus. Obviously, when I add these 2 equations or these 2 equations, 6 and 7 or 5 and 6, you would notice
L1 there in W1. L1 by L.
sorry. Yeah. Happy that you're very active. Lunch time has not dampened your enthusiasm. I'm very happy. So that's L1. So now, obvious that when I sum them up, WF plus WL has to be W, and that's what has happened here. So you see a minus sign here and a plus sign here, which we experience every day when you do an acceleration, that there is your weight actually goes back, or there's a redistribution of weights, okay, in the vehicle, and so the front wheel loses some of the reactions, and the rear gains this reaction, okay. So sum of them is equal to 0, okay. Simple. I don't think there will be any questions on this. We will go to the next step. Now, yes, we have written acceleration. You see in every advertisement of cars that 0 to 60 in 6 seconds, or 0 to 90 in 8 seconds, and so on and so forth. Okay. So what are the limitations of this driving force, or F? Okay. Can I have unlimited F? Okay, that's our first question. Or is it limited? Or is there a F max? Of course, the tractive force, as it is called, is controlled by 2 things. One is the ability of your power plant or the engine to generate the kind of torque, okay, which is applicable or which is available at the wheel. That's the first thing. Maybe your car won't be able to develop it. That's the first thing. But more important thing is the ability of the tire to take that force, okay, the FF. Without what would happen if it's more? Okay, you would have seen it that, for example, if it's a wet road or an ice, when you have traction, okay, the wheel starts rotating, slips, okay, major slip. We have to be very careful in using these terms. Slip has another meaning as far as the tire is concerned. Right now we say that we use a word, English word called slip, but we will then refine it when we study, okay, tires, right. So, the ability of the tire to support that force, traction force, or in other words, the tire without, as you said, slipping. So, the tire is the next reason for it. So, we can write that the F max, okay, in an analogy to the Coulomb's friction, we can write this to be mu into W. Analogy to Coulomb friction, we can write it as mu into W. Is it Coulomb friction that acts? Is this mu very similar to what I know, okay, a box sliding, okay, and a friction coefficient mu acting, okay. These debates are very important and interesting, and we will go into those debates when we look at tire mechanics, okay. So, when I say mu into W, mu is a sort of a dumped quantity, okay. So, mu is equal to or equivalent, I would say equivalent Coulomb friction, okay. So, that law brings us to the difference between a front wheel drive and a rear wheel drive. So, obviously, when it is a front wheel drive, okay, or both, it can also be 4-wheel drive. Let us now look at only the front wheel and the rear wheel drive, okay. So, mu is equal to Wf, which is the front wheel drive maximum force, and if it happens to be a rear wheel drive, then mu Wr will be the maximum force. So, what I now going to do, I am going to do is to now substitute for F, it is a front wheel drive or a rear wheel drive, okay, mu Wf is equal to F max, okay, I will substitute for F there here, okay, if it is a front wheel or a rear wheel drive, and then rearrange these quantities, so that I will know what is the F max or A by G. Very simple now. The first step is I will just substitute in this equation. Let me call that as 8 and 9. Okay, substitute equation 6 there, and I will rearrange the terms for F max, okay, because there is an F there, rearrange the term F max. So, I will just write down what is F max. You can do that as an substituting, okay, or using, I will say using 6 into 8, 6 and 7 into 8 and 9 if you want. So, I can say F max, maybe you can quickly do that, okay. That is for a front wheel drive is equal to mu W into L2 is there. So, W I have taken it out. So, L2 plus Fr into H, okay, there is an L there divided by W. Since I had rearranged the terms, I will get divided by 1 plus mu h by L. So, this is the maximum force that is developed, okay, if it happens to be a front wheel drive. If it happens to be a rear wheel drive, I will do the same thing with the second equation and I will get something like this for the rear wheel drive. The maximum F max is equal to mu W into L1 minus Fr into H divided by L, whole thing divided by 1 minus mu H by L. Okay, verify this. I hope this is correct.
The W will not be counted for the L minus F or H.
L minus, no, L1, sorry. Mu W into, yeah,
W into L1 minus F or H. Sorry.
minus Fr into H divided by L.
W into L1 separately. W will not be.
No, we had substituted, please note, we have substituted RR by Fr into W. So the W is what we are taking it out. So that's why we get a W here. Okay, if I had put RR, then it wouldn't come. Right? Okay. Right, that's L1. Now, this is the front wheel and the rear wheel drive, the maximum force that is developed. Okay. So, beyond this, the wheel will not develop a force, okay, and we will not be able to reach the kind of deceleration that we want. Okay. Now, what we are going to do is to change track and look at braking. Okay. So, this is the maximum force and braking becomes very important and we will change it and look at braking. The forces that are acting, all other forces are the same for braking except that there is not going to be a traction force, but there is going to be a braking force. So, the braking force will be in the opposite direction. So, that will be the braking force FB front and that will be the braking force FB rear. Is that the only difference? One more difference is that we are going to decelerate. Okay. So, I will replace, though it is not the right thing to do, it is not theoretically very correct, I should have A and put it as minus A, that is what I should be doing. But just for ease of understanding, every time you have to look at A, then you have to say that actually I am in minus A when I am braking, plus A when I am accelerating and so on. I will replace A minus A by D. Okay. So, I would replace A with D, where D is nothing but deceleration. That makes my job much simpler. So, when I am decelerating, what happens to my D'Alembert's force? Then it will be in the switch. This will switch. Right? Now, let us write down same thing. I am going to follow the same procedure, nothing very difficult or okay. So, let us write down the forces. Why not you do that in a minute? You know, you can very easily look at this. So, the only thing I am going to write, the first equation is W by G into D I will write, okay, is equal to rolling resistance force RA then what is that it's opposing? I will put this as plus or minus w sine theta. Okay, you know the physics. Okay, so that would be the second opposing force, and rolling resistance force is now opposing the motion, and of course I have the braking force, the front braking force plus the braking force, the front braking force, the rear. Yes, I am neglecting the drawbar pull this because I didn't want to add some more onto this. Yeah.
If D is positive here, we are still accelerating upwards.
No, I am. That's the accelerating direction. I am now decelerating. Okay, I am decelerating. So I'm braking. So I assume that I am decelerating. Assume in sense that I am of course decelerating. Okay, so the deceleration, okay, is written like this. Actually, how should I write this? I should have written like this: W by G into A is equal to minus, okay, RA minus and so on, RR and so on. Okay, so what I have done is, actually I should have written it as F is, when I write F is equal to MA, if I write the directions here, I am explicitly writing the directions here. Okay, obviously A will become negative. Okay, hence I am replacing that negative A with D. So in other words, I am replacing all the negative forces by plus forces. Okay, just to understand this, that's all.
Because like on what you have written A, you are replacing with D.
No. Please note that minus A is what I am replacing with D. I said I won't use the symbol A, but I'll use it D. Okay, D is equal to minus A. That's what I said. Okay, if you want minus A is equal to D. The symbol D indicates deceleration. Obviously, it is minus A. There's no questions about it. Okay. Do the same thing. Take the moment about A, moment about B in order to find out the WF and WR. Okay. I'm not going into those details again. I hope, I'm sure all of you can do that. It's not a problem. So I will only write the final result for WF. Okay. And this will be 1 by L into what will be the case, W into L2 minus or plus. It has to be plus because the force transfer will be such that there will be more load to the front when you decelerate. So this will be plus H into FB, the total, I am putting this as a total braking force, plus FR into the W. Right? So you can write that, once I write this, you can write WR. Okay, so I'm skipping steps here. So this is on braking. And so I am calling that as 1. I'll call this as 2. I'll call this as 3. Strictly speaking, I have to split this. I'm going to do that as FB front plus FB rear. the maximum braking force, which I would call as FB F max or F max braking force in the front, and the maximum braking force at the rear are similarly controlled by mu, okay, because it is that quantity called friction which gives the ability for the braking force to be developed. You know this all the time, okay, and so that is equal to mu into Wf, and maximum braking force at the rear is equal to mu into Wr. Now, this is an interesting factor here. This is an interesting factor here. In the previous case, we looked at the vehicle and said it's a front wheel drive or a rear wheel drive. Now, we can't do that in braking because braking is applied to both the wheels. Okay. So, if I say that the total force, braking force is Fp, a fraction of the total braking force is applied to the front and a fraction of the braking force is applied to the rear. Okay. Let me call that fraction as front to be kbf into fb, and the fraction at the rear to be fbr. So, kbr into fb, obviously kbr has to be 1 minus kbf. So, the key question which we are going to answer in the next class is how should the braking force be distributed between the front and the rear. Okay, that is the question which we are going to answer in the next class. Okay, stop here and we will continue in the next class.